things on here. Basically, when we're looking at the phase diagram, it's typically a diagram where the y-axis is your pressure, x-axis is your temperature. It doesn't matter what unit you use, it's pressure and temperature. And this line here at pressure equals to 1 atm, reading it along that 1 atm line will give you what is the normal melting point and what is the normal boiling point. So in this case, we're looking at water, right? So you're expecting the normal melting point to be here, which is this 0.0025. And the normal boiling point for water is 99.974 degrees Celsius. Alternatively, we have two more points that's of special interest for us. One point is my point A. So this is called my triple point. Right, so what is at the triple point? So whenever we're looking at these lines, we're saying these phases are at equilibrium, or there is like reversible phase transfer along the line, crossing the line. So in this case, when we're at the triple point, we're saying all three phases are in equilibrium with each other. Right, so related to the phase rule that we derived before, we have F equals to C minus P plus 2. Right? So C is a component. In here, for any one component system, your C equals to 1 and your minus P plus 2. So the maximum number of phases can be in equilibrium with each other for this one component system is 3. So hence the triple point. And then another point that's of special interest is our critical point. Right, so prior to the critical point, there is still a line telling you this is a liquid phase, this is a gas phase. But after the critical point, your liquid and gas phase are indistinguishable with each other, and hence those are like beyond what we care about. What else do we know? Now, in our last lecture, we started by talking about how to plot like a GM, the molar Gibbs free energy, as a function of pressure for this curve. We did the beginning of it together, so today let's just finish doing it. Again, what we're trying to do here is plot your molar Gibbs free energy, GM, as a function of pressure. So remember what we did before. I'll just do it one by one. Now, thinking about assuming our gases are ideal and assume our volume of the liquid does not change with small pressure change. So from this R to S point, we're assuming gases are ideal. So we know several things regarding that ideal gas. So from my R to S, we're talking about ideal gases. Can you see it without the light? Or do you want me to pull? Okay, looks good? So we're talking about ideal gases. And this process is a pressure change. All right. And in here, what do we know? We have ideal gases, reversible pressure change, so we can use what we derived before for this process. Now we're looking at the dGm as a function of negative Sm dt plus Vm dP. That's our Gibbs equation. Right. Again, we're trying to make a link, in this case, between your one component phase diagram to the Gibbs equations, the change of the thermodynamic state functions, things that we discussed in chapter 4 and 5. And for this pressure change, again, we observe the figure will be like from R to S, it's a straight line. So my temperature is not changing, so this is an isothermal process. All right. So what that means is my dP equals to 0. My first term is vanished. And then we have the expression of dGm equals to Vm dP. And do we know what's this Vm for our ideal gases? We do, right? So ideal gases, you have PV equals nRT. And T is a constant, N is a constant. We can write my Vm as a function of pressure. That equals to RT over P dP. All right. So on the plot, we are looking at expressing Gm, or the molar Gibbs free energy, as a function of pressure. So we're looking at Gm as a function of pressure. So naturally, instead of writing the dGm, you want to do integration of both ends to get an expression of Gm as a function of pressure. I have the integration of my dGm. So this one is the indefinite integration. I'm trying to get a mathematical equation as the answer. That equals to the RT over P dP. So we can write this one as my Gm equals to RT is constant, take it out, ln P, natural log of P. All right. Or the other way to put it, on my diagram here, when my pressure is at point R, to my pressure at the larger one, which is point S. Or can write this one is my R, this one is my S. So between my R to S, this is likely to be a natural log function. So if we plot the natural log, it's something look like this. Right, and we can write in this first part, you have Gm equals to RT natural log of P. Right, so far so good. Like this part is like nothing new. We're using everything you learned before. We're trying to make a connection in how to do it. Okay, so that's from R to S. What about at point S? What do we know about the position at point S where my phase change is taking place? Right, so now what we know is given the pressure at point S, we want to know, like, is this curve a continuous curve, right? What is the value of my molar Gibbs free energy at the point where your phase transfer is taking place? So what do we know about it? In this case, we're talking about the phase diagram or the equilibrium taking place at that point S. So at phase equilibrium, at equilibrium, what do we know about the chemical potential of your species? Well, the chemical potential must be equal to each other because they're at phase equilibrium. Or we have the chemical potential of your H2O vapor equals to the chemical potential of your H2O liquid. Right. What else do we know? This is a one component species. So for each component, we have the molar Gibbs free energy of my vapor equals to the chemical potential of my vapor. And this again goes back to the definition of chemical potential. So if we write the full definition of chemical potential of species I in phase alpha, so that's the partial differential of total Gibbs free energy over the Ni in phase alpha, while keeping like P, T, and your nj doesn't equal to I as constant, right? So those, again, goes back to what we learned before. When we're talking about using the actual definition of chemical potential, it'll be like, okay, there's only one phase. We're only looking at the vapor phase or the liquid phase. So looking at only one phase, we can drop this alpha, because it's only one phase. For one component, we can drop this I, and also the requirement of the rest of the species kept constant. And then we have, for the one component, one phase species, your chemical potential equals to the molar Gibbs free energy. All right, so this can easily be a true and false problem in whether or not it is true. And in this case, because we know the chemical potential of your vapor equals to liquid for your water, we also know for the molar Gibbs free energy of your water vapor equals to the chemical potential of your water vapor, the molar Gibbs free energy of your liquid water equals to the chemical potential of your liquid water. So taking together, we have the Gm of your H2O liquid equals to the molar Gibbs free energy of your H2O vapor. Or at this point, even if we have the phase transfer taking place, the number of my molar Gibbs free energy must be the same. So it's a continuous plot. Yes. Oh yeah, sure. Okay. Much better. And then thinking about what's happening at the very end. Now we have the liquid. So we're using the same logic before, right? So we have from my S to Y. Again, this is the change of thermodynamic state of my pure liquid water. Right? So we can similarly use the equation of dGm equals to the Vm dP. Remember, because for isothermal, your dt equals to 0, so the other SDT term becomes 0. Now, in this case, we're making the assumption that the volume of the liquid does not change with relatively small pressure increase. So that's the assumption we're making here. That means my volume is not dependent on pressure. So if we take the integration on both ends, we get the Vm dP, and we end up getting Vm integrate of pressure. So your Gm equals to Vm times pressure. All right, so if my Vm for the liquid is considered to be constant for the small pressure change, then this becomes just a linear equation between my pressure at my final point y. And in this second sequence, we have Gm equals to Vm times pressure. Yes?
Or as to why don't you replace Vm with an R over P?
Well, so thinking about where is my point y, or where is my point S and Y, what is the phase of the species we're interested in? Okay, so where does the PV equals nRT comes from? So why are we not using it, right? So lots of the time, don't ask the question why we're not using the equation. Really thinking about what is the physical meaning when we're talking about these points on the diagram. The phase diagram is telling us a lot of information. It is our responsibility to read it and use the appropriate information. But there's one question we could ask, which is, what is my Vm? Right, so in this case, what is my Vm? Now we know my Vm here, we're assuming it's not changing for my liquid. So the other way to put it is this one, we can approximate it using my RT we're trying to approximate it at that point of the PV equals nRT. But this pressure here is my pressure at point S, where we can still treat it as the ideal gas. All right, how are we feeling about this? So this part is, again, this is one of those lectures that you feel it's super easy when I'm doing it with you, like thinking about how we can ask this question in a different way. We can replace this phase diagram with, let's say, now we have 3 solid phases in equilibrium with each other. We can give you the equation of state of all 3 phases, and do you still know how to do this kind of derivation? Or now, instead of asking from R to Y, what if we're going from here and you have like a curve going from the gas to the solid phase, and what kind of approximation we're making? So those are the questions you can potentially ask yourself when thinking about these questions. All right, so that's a one component phase diagram. It looks straightforward. Know how to read the diagram, know what each section of the diagram mean, and also know how to connect what we learned before into the one component phase diagram. And now let's look on to see the next question, which is, well, how exactly are these curves being measured, and how are they related to experimental setup? And, well, how can we better use it? So that's the Clapeyron equation. That's going to be our last new material, which is the Clapeyron equation. So I'm giving you the expression of the Clapeyron equation at the beginning, and then let's think about how exactly is the Clapeyron equation being derived. I'll write the Clapeyron equation on the board, and then we'll do the derivation together. Again, like all derivations, we start by doing the derivation. That's conceptually important, and then talk about why do we care about it, and then application of the Clapeyron equation. Well, the why do we care about it is actually pretty straightforward in this case. We want to know how that phase diagram come from. So in this case, we're talking about a relationship between how your pressure change with respect to temperature for one component and two-phase equilibrium. And in this process, we'll make lots of approximations just to make the derivation easier for us. Okay, so let's thinking about it. Now, looking at what we have here, imagine we have a phase alpha and phase beta on my plot of pressure versus temperature. So in here, the line tells you here is the equilibrium between your phase alpha and phase beta. We only have one component. So where do we get started? First of all, on the right-hand side, we have my enthalpy, or some kind of thermodynamic state functions. And on the left-hand side, when we're discussing phase equilibrium, we're talking about chemical potentials. So first thing first, let's just translate our chemical potential into my Gibbs equation, or the Gibbs free energy. So this one, we're just saying, using the fact that my mu alpha equals to mu beta along the curve, and we just do the derivation for the one component, one phase, your mu alpha equals to gm alpha, and your mu beta equals to gm beta. Or the other way to put it is, because these two are equal, we can write my, yes.
Sorry, is that GN alpha?
GM. So in this case, we can write my GM 4.1 in phase alpha equals to molar Gibbs free energy in point 1 in phase beta. So I'm focusing on my point 1 here. All right. Now, what is the difference between my point 1? So this is my initial point. And then we want to express my point 2 as a function coming from point 1 using the differential equation. So what that means is we can write my GM2 in phase alpha equals to GM1 in phase alpha plus D GM alpha. Likewise, if we're looking at my GM2 in phase beta as GM2 phase beta plus the infinitesimal change of Gibbs free energy in your phase beta, dGm beta. And these two terms are equal to each other, like the same derivation we did before. They're aligned the equilibrium curve, so they must be equal to each other. And then in our previous derivation, we also went over the saying of, say, now this term, the GM1 alpha and GM1 beta. Okay, 1 second. I'm just checking what I write here. Okay, so these two are equal to each other. And consequently, these two must also be equal to each other. Yeah.
Would it not be GM1 beta plus DGM beta?
Yes. Thank you. So these two terms must also be equal to each other. And since we know these two are equal to each other, we eventually end up to say, okay, so the differential of my molar Gibbs free energy change for both phase alpha and phase beta must equal to each other. So we end up saying my dGm alpha equals to d GM beta. So far, so good. And then taking it with our Gibbs equation. So for our Gibbs equation, we have my dGm equals to negative Sm dt plus Vm dp. So in this case, I'm just plugging in these two terms into here. We end up getting the negative Sm alpha dt plus Vm alpha dp equals to negative Sm beta dt plus Vm beta dp. So keep in mind, we're trying to find a relationship between my dp and dt. So let's just move the terms. So my dp goes with dp and dt goes with dt. All right, so the reason we're moving the term is because I want my dp and a relationship between my dp and dt. So what does that mean? So that's simplify this one to be my Vm alpha minus Vm beta dp equals to Sm alpha minus Sm beta dt. All right, simply moving the term. So my dp and dt goes with each other. Now I can focus on my dp and dt to write it as dp over dt equals to the Sm alpha minus Sm beta over Vm alpha minus Vm beta. Or the other way to put it, that equals to the delta S molar, the entropy change, the molar entropy change over delta S Vm, the molar volume change. And then since in this case, in both cases, we're dealing with the same number of moles, so we can drop that molar because the number of mole will cancel out. So my Sm equals to S pi divided by N. My Vm equals to V divided by N. So my number of mole will cancel out. So we end up getting my delta S over delta V. All right, so again, we're trying to find the curve of dP over dt describing this two-phase equilibrium, or we're talking about reversible phase change happening. What else do we know about reversible phase change? So in our previous discussion, when we're talking about calculation of entropy change for reversible phase change. So this is back in chapter 3, 3.25. We have derived that delta S equals to delta H over T. And that temperature is the temperature of the phase change where it's taking place. Or at the end, we derived my Clapeyron equation to be my dP over dt equals to delta H over T delta V. Or you can write it in the molar version. It doesn't matter. It's the same because the number of mole will cancel out. So that's the quick derivation of our Clapeyron equation. All right. Not hard at all, but it looks a little bit horrible. How are we doing so far? Doing good? And now let's think about how exactly are we using the Clapeyron equation to describe the phase equilibrium. So let's look at two scenarios. First scenario, let's considering the liquid vapor and solid vapor equilibrium and see how do we use the Clapeyron equation in a more general fashion. So for this process, what our goal is deriving a general formula of whenever I'm changing the pressure, well, how do I expect the temperature to change along with it? And in this process, we're making a few approximations so that our calculation is straightforward. So the Clapeyron equation is listed on the board, so we'll be using it. But before we do that, let's just think about what are the systems we're dealing with. Now, in my Clapeyron equation on the bottom, we have the change in the molar volume. So this term comes to our first approximation that because the molar volume of our gas is way larger than the molar volume of our liquid and solid. It's a fact, right? So gas in general, the molar volume is much bigger compared to the molar volume of your solid and liquid. So that means we can come to our first approximation. That is my delta Vm, or the change of your molar volume when the phase transfer is taking place, equals to the molar volume of gas minus the molar volume of your liquid or solid. It's roughly equal to the molar volume of gas. So this is my first approximation. All right, so whenever you see this kind of curve, it's hinting like, okay, we're making an approximation. So that's why when we're dealing with like very dense gas, or when we're approaching the critical point, then these approximations no longer hold. Remember, at the critical point, your liquid and gas becomes indistinguishable with each other. So some of the question might be like in a true and false problem, or be like, we make this approximation in the process, and it fails around the critical point. Why it is the case, right? So knowing that it failed because the volume, the molar volume of the gas and liquid becomes similar to each other, so this approximation no longer holds when we're approaching the critical point. And the second approximation is also related to what we already do. So that's assuming my gas behave ideally. Alternatively, we could also give you like a Van der Waals gas equation and assume it is a Van der Waals gas, just making math a lot more complicated. Using ideal gas laws just to make our calculations easier. So by using these two approximations, how can we simplify the Clapeyron equation for this liquid vapor or solid vapor equilibrium? So thinking about what we have dP over dt equals to my delta Hm over T delta Vm. So here my purpose is to represent my Vm as a function of temperature and pressure, because after all, on the left-hand side, we only have pressure and temperature. So in here, we can approximate this one to be my delta Hm over T times pressure over RT. That's from my ideal gas law. And if we're making the assumption of, well, let me simplify this first. That equals to P delta Hm RT squared. In this process, we still have my enthalpy, the change of enthalpy, the delta Hm involved. So we need to make our third approximation. That is my delta Hm as constant. Along the equilibrium line, not close to the critical temperature. So with this, we can do a little bit more calculus here. So on the left-hand side, we have my dP over dt roughly equals to, on the right-hand side, my P delta Hm over RT squared. So this is a little bit like the Van 't Hoff equation, so we're doing the same kind of operation here. So using calculus, we know my D 1 over T over dt equals to negative 1 over T squared. And my D ln P over dP equals to 1 over P. So the left-hand side, the dt over dP, thus becomes, so my dP equals to my P d ln P. And on the bottom, we have my dt equals to negative T squared d 1 over T. And on the right-hand side, we still have my P delta Hm over RT squared. We can cancel out some of the terms. We end up with our final expression that my D ln P over D 1 over T is roughly equals to the negative of delta Hm as a function of R. And if you do the integration on both ends, you can find a way to solve for pressure change and temperature. Or if we finish by doing that. We have the integration of d ln p roughly equals to the integration of negative delta hm over r d 1 over t, or we solve it. Yes.
Why did you cancel the p and the t squared?
Because this one, dp over dt, becomes the p d ln p, so that's here. And then the dt becomes the minus t squared d 1 over t. So the whole point here is your pressure over temperature is a relatively complicated equation. So if we're doing the experimental measurement of plotting your pressure over temperature, you'll end up getting a curve. But it's a little bit hard to interpret it, what's behind that curve, because the relationship is more complicated. So that's why scientists want to get linear relationships. And we use calculus to say, now instead of plotting pressure with temperature, if we plot the natural log of pressure over 1 over temperature, you'll be able to get a linear number. And let's see one application of this relationship together. And that is, well, let's say we give you the normal boiling point of bromine gas as 58.8 degrees Celsius. And its vapor pressure at 25 degrees Celsius is 0.2870 bar. Ask you to estimate the average delta Hm vaporization of bromine gas in this temperature range. So to set up this problem, the easier way to say is, well, let's just make them on the figure and see what do we have. So if we have my pressure and my temperature on the y-axis and the x-axis, we have the normal boiling point is 58.8 degree. So that is when my pressure equals to 1 atm. My boiling point is 58.8 degrees Celsius. Alternatively, we have the vapor pressure at 25 degrees Celsius is 0.287. So if my temperature is 25 degrees Celsius, the vapor pressure is 0.2870 bar. All right, so the question asks for this delta Vp. So using my Clapeyron equation, we can come back to this one. So we did all the derivation before, and now we can finish this derivation to say we end up getting ln P2 over ln P1 roughly equals to the negative of delta Hm over R 1 over T2 minus 1 over T1. All right, so before we can plug in the numbers, you just have to clear out the unit and then plug in your P2, P1, T2, and T1 into the equation using the equation of the ideal gas constant R to calculate the delta Hm of vaporization. So for this one, when we're actually doing that, we have my, let's say this is my P1, and this is my P2. Or this is my point 1, this is my point 2. So what do we have? Is we have P1 equals to 0.2870 bar, or roughly equals to 0.283 atm. We'll give you the unit conversion if needed in the question. Yeah.
I think if you just slightly
Wait, why is it so narrow? Okay. All right. And we have my P2 equals to 1 atm. And for temperature, it's the same thing. We just have to convert it into Kelvin temperature. So my T1 equals to 25 plus 273.15 equals to 298.15 Kelvin. My T2 equals to 331.95 Kelvin. And then it's just plug in the numbers and calculate for delta HM. For this kind of calculation, there is a chance we'll ask you, after you do the calculation, we'll ask you what are the approximation you made in order to solve this problem. So these approximation are the 3 approximation we used in the previous case to get to this expression. Remember, what are the 3 approximation? First approximation, we're saying your molar volume of the gas is way larger than the molar volume of your liquid or solid. So we're not close to critical point. Second, we'll approximate my gas is behaving ideally, again, away from critical point. Third approximation is that delta HM is a constant along this equilibrium line. Again, very far away from the critical point temperature. All right, so there's a chance I would ask you to do the calculation and to state what are the approximation you made in order to get to the answer. So know where the equation comes from, know how to use the equation, and again, keep in mind, we're making approximations, so these equation will fail when we're getting close to the critical point temperature. Okay, and there's like 2 more practice problems I don't think I have time to go over. I'll go over with you tomorrow. And then after we do those 2 practice problems together, those will be the end of all the materials of our quarter. So in our tomorrow's lecture, we'll do 2 problems finishing up on the Clapeyron equation. And then I'll do a quick overview on all the topics we discussed in this quarter and see how they're connected with each other. So for my recorded lecture, it's likely to be a walkthrough of the previous final exam. All right, I'll see you tomorrow and in class or in office hour.